Welcome to the special plenary session, the top 10 greatest challenges facing the world ocean. I'm your host, Dr. Chris Verlinden, oceanographer and co-chair of this year's GEO 2050 event. Today we will be discussing 10 topics of concern for the world ocean, 10 ways in which the ocean is changing, and not for the better. But there is hope, and we will also be talking about what you can do about every single one of these topics. The 10 topics of concern today are ocean acidification, global ocean warming, sea level rise, sea ice loss, coral reef loss, ocean deoxygenation, mangrove deforestation, ocean plastics, ocean noise, and overfishing. 9 of the world's leading experts in their respective disciplines and I will be discussing each of these 10 challenging issues. My colleagues here today represent leading international experts and exciting rising stars in the community. I will be starting off today's session by discussing a topic that is near and dear to my heart. I wrote a paper a few years ago discussing a proposed method of remote sensing of ocean pH using acoustics. And the next topic was my primary motivation. Ocean acidification is one of the most fundamental and straightforward topics we will be discussing today. Now, in order to understand ocean acidification, we need to first talk about what is meant by the term acidification. Not surprisingly, the term acidification refers to when a fluid, in this case the ocean, becomes more acidic. But what is meant by the term acidic? Well, acidity is typically measured on the pH scale, which ranges from 0 at the most acidic to 7, which is neutral, and 14 at the most basic end of the scale. To put it in terms of household chemicals, which you might understand and be familiar with, vinegar, a common household chemical, has a pH of 2.5. And since that 2.5 is lower than 7, lower than neutral, that means it is very acidic. Sulfuric acid, which you might have heard about in high school chemistry classes or even used, has a pH of 2.75. On the other end of the spectrum, we have baking soda or sodium bicarbonate, which has a pH of about 8.3. And again, since that 8.3 is higher than 7 or greater than neutral, that is a basic chemical. Milk of magnesia or magnesium hydroxide has a pH of a whopping 10.5, making it extremely basic. Now that we understand the term acidification and what is meant by acidity, we need to talk a little bit about how and why the ocean is becoming more acidic. Well, it's fairly straightforward. The cars we drive in, the planes we fly in, and the power plants that produce our electricity all produce carbon dioxide as a byproduct of the combustion reaction which fuels these cycles. And that carbon dioxide then spreads around the world ocean and comes in contact with seawater everywhere. And when carbon dioxide comes in contact with seawater, it dissociates into carbonic acid and bicarbonate and free hydrogen ions. Now, the definition of pH that we didn't discuss earlier, the strictly mathematical definition, is the inverse logarithm of the concentration of free hydrogen ions in the fluid. So what that means is if we increase the level of free hydrogen ions, we make the fluid more acidic, dropping the pH. So as we produce carbon dioxide, that carbon dioxide interacts with the ocean, dissociates into carbonic acid, which as the name suggests is acidic, which raises the concentration of free hydrogen ions, thereby decreasing the pH of the ocean, making it more acidic and overall a less comfortable home for marine organisms that rely on a fairly basic or neutral ocean for their well-being. You don't need to take my word for any of this. Today we're going to do a very brief demonstration in the laboratory of ocean acidification, starting with a combustion engine, exposing seawater to that combustion engine, and watching what happens, watching the pH drop. Thank you very much. So we're going to start off with a sample of seawater right here. I am going to pour the seawater into 2 equal sample vessels. So you can see that both of these samples of water come from the same source and have the same initial pH. I'm going to measure the pH using this pH sensor, where this probe is inserted into the water, and on this screen, which we'll zoom into, you can see the pH of the fluid. So I'm going to insert the probe into the water right here and measure the pH. And if you zoom in, you should be able to see that the pH is a little over 7. Now it's dropping a bit, and I bet it will actually equilibrate out to just under 7. But the water that comes out of your tap is fairly neutral. Now what we're going to do is we're going to inject water into one of these, CO2, into one of these 2 sample vessels, and we're going to measure the pH as we do that. Now if you want to do this at home, let's say over Thanksgiving with your family, You could use something a little bit less expensive, and these pH test strips used for pools or hot tubs will work just as well for your purposes. Now, in order to get CO2, you can blow bubbles into the water with a hose. That's not very much fun. It doesn't really illustrate the internal combustion part of this whole problem. So I'm going to use this highly scientific leaf blower here. Now, remember, you might not want to try this part of it at home because I am a professional physicist, but still counts. So I'm going to start up my CO2 generator here, my highly scientific device. So you can see if you zoom in that just by running it for a few seconds, we were able to drop the pH to about a 6.5. We probably could have gotten it a little bit lower if we ran it for longer. Just to show you that it's not a trick, we will dip the pH sensor in that original sample of water, which remember came from the same sample vessel, and you'll see the pH on the sensor rapidly increase to closer to 7, back to neutral. So you can see that by running a combustion engine, which produces carbon dioxide just like your car, just like the planes you fly in, just like a power plant, and exposing seawater to that CO2, we were able to drop the pH, and in this case to a level that would be difficult to survive for many marine organisms. Thank you very much for that demonstration. You can see that that was done in my basement. The demonstration that we just saw showed the acidification process from a combustion engine to producing carbon dioxide, lowering the pH of a fluid, causing it to become more acidic. So we now understand the chemistry behind ocean acidification. Now we need to get a handle on the scope and scale of the problem and the current state of ocean acidification in the world ocean. Well, as you can see from this chart, a plot of ocean pH and CO2. On the y-axis on the left side is concentration in parts per million of CO2 in the global world atmosphere. And on the right-hand side is the average sea surface pH across the world ocean. So you can see between 1960 and 2010, the concentration of CO2 in the atmosphere due to the anthropogenic production of CO2 has raised from 300 parts per million to nearly 400 parts per million. And over the last 20 years of that same time period, the average surface pH of the ocean has dropped from about an 8.1, which is fairly basic, to an 8.05, which is still basic, but less basic. And that represents a very significant change because remember, pH is a logarithmic measure. So 0.05 is significant. And what's more significant is if we carry those trends forward to 2100, you can see by the red line in this plot that it is anticipated that by 2100, the global average sea surface pH will decrease to 7.8 if we do nothing to change our current output of carbon dioxide. There is, however, a silver lining to this cloud because from what you can see on the blue line, if we curb our CO2 emissions significantly, then we can stop and even reverse this trend, increasing the sea surface pH back to natural levels. Now, in order to see this more visually, I want to show you this plot of global sea surface average pH in 1850. Now, this is estimated because we didn't have all the same measurement instruments, but I want you to see that the average ocean pH at the surface is well over 8. It's very basic. And this map is dominated by dark blue colors. And there's a little bit of light blue and certainly nothing going into the yellow on this particular color bar. Now, if we advance to today's ocean pH, we can see that the ocean is still largely basic, but less so. The average pH you can see is still just a little bit over 8, but only a little bit. and it's not a uniform distribution. The Pacific Ocean tends to be a little bit more acidic than the Atlantic Ocean, for example, and that's not necessarily of concern, because organisms that have evolved to live in these locations have evolved to live under these current acidity conditions, and that's okay. But now, if we look at the anomaly, which helps us understand what the trend in ocean pH is, it's a lot more concerning. The ocean pH anomaly, represented here in this plot, shows what would happen if we subtracted our current ocean pH from the average pH over the last 200 years, representing the pH difference between now and what has been the average over this period. And if we look at the anomaly, we can see that everywhere on this plot, the anomaly is negative, which means everywhere in the world ocean, the pH of the ocean is decreasing, meaning the ocean is becoming more acidic. And again, not uniformly. If we look at these red and orange numbers in the North Atlantic, the ocean pH in these areas has dropped by 0.12. On a logarithmic measure, this is an extremely concerning trend. And if we carry that trend forward, as you can see here in this plot, and show what the ocean sea surface average pH is expected to be in 2100, contrast this with the plot we saw a few slides ago of a dark blue basic ocean everywhere. We see this ocean is almost entirely light blue and even yellow, meaning the ocean is going from being extremely basic to almost neutral. And you might ask yourself, why does that matter? Neutral sounds okay. And on the surface, you're correct. But as is probably not surprising to you at this point, the chemistry of how biological reactions that marine organisms count on to survive has evolved over the millennia is for the current ocean conditions. And this is perhaps best represented by a measure called the aragonite saturation state, which you can see from this equation is basically the concentration of free calcium and carbonate ions divided by their equilibrium concentration. And what that essentially means is it represents a bioavailability of this type of calcium carbonate for chemical reactions such as organisms building their calcium carbonate shells or tests. They're building their homes. And so what you can see based on this plot of the aragonite saturation state in 1850 is that the vast majority of the ocean has a fairly positive aragonite saturation state on the order of 3. That means organisms can build calcium carbonate shells in the vast majority of the ocean. Now, if we continue the pH trend that we saw on the previous charts forward and look at the aragonite saturation state projected in 2100, we can see these massive regions of the world ocean which are orange and even red, which are areas where organisms would have a difficult time forming calcium carbonate shells and therefore would be unable to survive. So in short, what this plot is showing is that by 2100, significant portions of our ocean will be uninhabitable to a significant number of marine species. So who cares? You're not a marine species. Well, for starters, salmon care. And anyone and anything that eats salmon, from a grizzly bear to human beings. Now, the reason that salmon care about ocean acidification is that salmon are what's called an anadromous fish species, which means they spend some of their time in rivers and some of their time in the ocean. And when they're in the ocean, they love to eat these little critters called pteropods. Now, pteropods are a pelagic, meaning they live in the water column, free-floating, not on the bottom or not on the surface. They're a pelagic snail species, which, as you've probably guessed by now, form calcium carbonate shells. And, as you've probably also guessed by now, if the ocean continues to become acidic at its current rates, they will be unable to form those shells in the future. They are one of those species I mentioned that will not be able to survive if the ocean keeps becoming as acidic as it is. So this will have what's called a trophic cascade, which means if there are no pteropods, the salmon that eat the pteropods will be impacted. And then all the organisms that rely on the salmon, including grizzly bears and ultimately human beings, will also be impacted. So, in short, everyone cares. Everyone who in any way is associated with this food chain, which is all of us. So at this point, you might be asking yourself, what can I do? The fact is, all of these trends are extremely concerning. And you might be asking yourself, what can I do as an individual, as a private citizen about this problem? Well, there's at least 4 things. The first thing you can do is support scientific research. What I mean by that is when there's a ballot on the election that says, should I increase funding or decrease funding for oceanographic research, particularly marine chemistry? The answer really needs to be increase at this point. The fact is, we need to understand this problem better. We need better sensors that can measure the pH of the ocean in situ. We need remote sensing technologies that can measure pH all over the world ocean so we can understand the current state of the problem and make more accurate predictions about the future so that we can be prepared for what the future of the world ocean holds. Second, support initiatives to empower women in demographics that are underrepresented in the scientific community. Now, it's not always immediately clear what the links are between some of these socioeconomic and often politicized issues and a scientific topic like ocean acidification are. But it's been shown by statistics that a more prosperous community that has more educated individuals has more minds working on solving a problem like this, and that is always a good thing. In short, support initiatives to empower women globally and underrepresented minorities in the scientific community. Third, reduce your personal carbon footprint. Now, I am not an expert in this particular portion of climate science, but I interviewed a lot of experts in preparing for this talk, and some of these things are very simple. You can drive less and take public transportation more. Eat less or even no red meat. Eat a plant-rich diet. Get solar panels for your house. Reduce your food waste. Fly less, and maybe buy carbon offsets when you do fly. Minimize new product purchases, or insist through your purchasing power on sustainable supply chain management in the things that you do buy. And maybe reduce your house temperature a little bit in the winter and increase it in the summer to reduce the amount of electricity and power that you use, among a great many other things. Finally, communicate about climate change. Many of you in the audience might be professional educators, in which case, educate. If you are not a professional educator, educate. Talk to your friends, talk to your family. Maybe bring up the uncomfortable topic of ocean acidification over Thanksgiving dinner. Because the fact is, those of us who understand the problem, which now includes you, have an obligation to do something about it. And one of the most impactful things we can do is to start a conversation and open a dialogue between everyone who will listen, which for all of us includes our inner circles, our friends, and our families. So in conclusion, support scientific research, support initiatives to empower women and demographics underrepresented in the scientific community. Reduce your personal carbon footprint, and communicate about climate change. Thank you very much. Like I said, ocean acidification is one of the most fundamental topics discussed here today because it is a direct consequence of the CO2 that we as people put into the atmosphere. Similarly, our next topic, presented by Dr. Greg Sennett, global ocean warming is a result of anthropogenic input of CO2 into the atmosphere. Dr. Greg Sennett is a postdoctoral researcher at the University of California, Irvine. An observational physical oceanographer, he studies processes affecting nearshore circulation, mixing, and stratification. As part of his research as an AAUS science diver, Dr. Sennett often uses equipment deployed in the dynamic nearshore environment to measure heat flux, internal wave dynamics, and other nearshore processes, with direct implications for coastal ecosystems. As an NSF fellow, Dr. Sennett has also developed high school earth science curricula focused on experimental learning techniques and making pioneering research accessible to and exciting for beginning scientists. Dr. Sennett earned a PhD from Scripps Institution of Oceanography in 2018 and holds MS and BS degrees from the University of Maine in oceanography and engineering physics. Thank you very much for being here today, Dr. Sennett.
Okay, thank you, and hello everyone. My name is Greg Sennett. I'm a postdoctoral researcher at the University of California, Irvine, where I primarily study coastal ocean processes. One of the ways that I do that is by measuring ocean temperature in ways that inform us about water mixing, transport, and other important physical aspects. Ocean warming is a significant challenge, so in the next few minutes, I'll try to briefly summarize the problem and then highlight some of the research and implications related to global ocean warming. By now, you're probably well aware of the factors that contribute to climate change, but if not, I'd encourage you to explore the Intergovernmental Panel on Climate Change, or IPCC, reports, which are an excellent source of accessible and extensively peer-reviewed climate and ocean science. One aspect of climate change that I find frequently surprises people is that the ocean has taken up more than 90% of the excess anthropogenic heat of the climate system. On the face of it, this may seem like a good thing, leading to less atmospheric heating, but as we'll see, that's not the case. These two plots from the IPCC Fifth Assessment Report summarize how the global ocean is warming. The plot on the left shows the evolution of globally average temperature difference from the mean of the top 700 meters of the ocean. And the map on the right shows the temperature trend of the top 700 meters over the same period. The IPCC, in conjunction with thousands of scientists around the world, conclude with certainty that the surface ocean is warming. And it's fair to ask how we know this, so let's explore some of the research behind this conclusion. Ocean temperature observations date back a very long time. Coastal observatories, ocean moorings, ship, and more recently, autonomous glider transects all record data at various locations and over a wide variety of depths. The observed ocean area vastly expanded in 1979 when satellites began to observe sea surface temperature. Modern satellites fly in coordinated orbits, making a wide variety of observations from the top of the atmosphere down to the surface of the ocean. And these data are publicly available, and I'd encourage you to go check them out. For example, a recent global sea surface temperature observation from the MODIS observatory on the Aqua satellite is in the lower right. Satellites observe only the surface ocean, however, and observations in deeper water are sparse, which is why the Argo program was initiated and has become so important. Since 2000, Argo floats have provided continuous observations of the ocean's top 2,000 meters. And as of a month ago, there were nearly 4,000 operational floats deployed by 24 different countries throughout the world. These data are also publicly available. So here's a plot from an instrument that I pulled at random, not too far away from where I am now. This plot shows depth on the y-axis plotted versus temperature, and it clearly shows the classic ocean temperature profile with warm, less dense water floating near the surface and cooler, denser water below. Of course, these data can be used to study many different processes, but how are all these measurements used to study global ocean warming? From a global ocean warming perspective, scientists are basically trying to understand three fundamental things. And that's, what is the heat flux through the ocean surface, both into and out of the ocean? How much heat is contained near the ocean surface? And at what rate is surface ocean heat mixed into the deep ocean? And these are three really important questions. The first question addresses how much heat is entering or leaving the ocean system. The second question addresses the temperature and habitability for organisms in the epipelagic or sunlight zone, where most of the ocean's biomass is contained. And the third addresses the rate at which the entire ocean heat content is changing. So let's now talk about a few implications for a warming ocean. Sea level rise is a direct consequence of the rising ocean temperature. As water temperature rises, the volume that water occupies increases related to the thermal expansion coefficient. And you can actually explore this and determine the thermal expansion coefficient for yourself. One experiment that I like is linked at the bottom. Sea level rise is a topic of another talk, so I won't say too much more about it other than to point out that thermal expansion is a significant contributor to the observed global mean sea level rise. Another direct implication of global ocean warming is increased stratification. As the surface ocean warms, the surface layer becomes less dense and the ocean becomes more stratified or harder to mix. Intensified surface warming has increased thermal stratification of the surface ocean by about 4%. And this map indicates the rate of stratification change around the world. Increasing stratification and the subsequent reduction in mixing is troubling since oxygen-rich near-surface waters are less likely to be mixed downward, and similarly, nutrient-rich deeper water can't be mixed to the surface photic zone where primary production can occur. Thus, increasing stratification is very likely to reduce primary productivity and fish stocks, according to the IPCC. And again, there are several experiments that you can try yourself to see how increasing stratification inhibits mixing. This is an experiment from the University of Maine that I particularly like. Marine heat waves are defined in a few different ways, but are essentially prolonged periods of abnormally warm water, partly due to the increased stratification and partly because of the extra heat in the climate ocean system. Marine heat waves have doubled in frequency, become longer lasting, more intense, and more extensive. The IPCC concludes that 84 to 90% of the marine heat wave events occurring between 2006 and 2015 were due to anthropogenic temperature increase. Here, the plot on the left highlights some of the more recent marine heat wave events and their attributable costs. Like ocean temperature in general, marine heat waves have far-reaching effects, even causing droughts, floods, intensified storms over land, in addition to the direct ocean ecosystem impacts. And you can monitor marine heat wave conditions on your own. For example, this map shows conditions recently on November 5th. Finally, let's look at how the global ocean temperature is expected to affect a wide range of ocean ecosystems. The plot here in the upper left panel shows the global mean sea surface temperature versus time. The brown line is the observed temperature with the current warming level above pre-industrial temperature shown by the horizontal gray line. The red and blue lines represent predicted temperature under two different climate mitigation scenarios. The red line is the predicted sea surface temperature under a business as usual scenario, basically doing nothing. The blue line represents the predicted sea surface temperature with aggressive climate change mitigation measures in place. The remaining colored bars here represent the degree to which ocean warming affects various ecosystems, with white representing undetectable effects and healthy ecosystems, and purple representing a very high ecological risk. So today, we're documenting adverse effects to the epipelagic, salt marsh, seagrass, kelp, and warm water coral ecosystems with high or very high confidence. But in just 30 years, at our current level of warming, all ecosystems, including the deepest parts of the ocean abyss, will likely be affected, with the most biologically productive and diverse ecosystems affected at high or very high levels. So that's just a very brief tour of the global ocean warming problem and some of the science behind it. The problem, like any potential solution, is complex, it's far-reaching, it's tied to climate change with impacts to global economies. And if there's any silver lining to anthropogenic climate change and global warming, global ocean warming, it's that it's anthropogenic. We changed it so we can affect change. And I've left this plot up to emphasize that point. There are personal choices that we can make to help mitigate both atmospheric and ocean warming, from eating lower on the food chain to simply being aware of and reducing how much energy and material we consume. We can also prepare for expected changes, such as sea level rise. And importantly, I want to emphasize that it's individuals who first spark systemic change, and that has real potential to move the climate needle. And ultimately, climate mitigation will involve governments, industry, and individuals. But science needs a seat at that table. And all of us can be an advocate for evidence-based science. The IPCC reports are a great place to start if you're new to the topic, and I encourage you to go check them out. I hope you found this talk helpful, and as you listen to others related to climate science and ocean science, I hope you'll continue to think about how you can take action. Thanks.
Thank you very much, Dr. Sinnott, for that informative talk on global ocean warming. The next topic we'll be discussing today is closely related. It's sea level rise with Dr. Gino Pasalakwa. Dr. Pasalakwa is an oceanographer, meteorologist, and fisheries scientist. He is currently a scientific advisor for the Save the Wave Foundation. Previously, he was a marine technician at UC San Diego and worked on board for the Scripps Institution of Oceanography Ships of Opportunity program. Before that, he worked as an associate technician at Universidad Autónoma de Baja California, where he implemented and developed a coupling system between WRF and the Regional Ocean Modeling System, or ROMS, for the study of air-sea interactions of winter cold fronts in the Gulf of Mexico as part of a research team for the CICESE, Petróleos Mexicanos, PEMEX project, mooring network in the deep Gulf of Mexico. His PhD studies looked at air-sea interactions of winter cold fronts over the warm waters of the Gulf of Mexico, analyzing momentum, heat flux, and moisture fluxes using the Weather Research and Forecasting, or WRF, model as a diagnostic tool. Dr. Pasalakwa has been a good friend, colleague, and collaborator of mine for over a decade, and I very much appreciate him being here. Thank you very much, Dr. Pasalakwa.
Hello, my name is Gino Pasalakwa. I'm a committee member of the Bahia de Todos Santos World Surfing Reserve and a scientific advisor for Save the Wave Coalition. And today I'm going to talk about sea level rise, implications for coastal conservation, and surf ecosystems. As it is well known by now, sea level has risen between 21 and 24 centimeters since 1880. As you can see from this map that you're looking at, the sea level change is not homogenic around the world. There's some areas that have higher sea level change, and there's some areas that have even a decrease in sea level change, mainly around Antarctica. How this translates for coastal environments. For example, in the US coastline, high tide flooding is now 300 to more than 900% more frequent than it was 50 years ago. And 2019 was the highest annual average sea level change in the satellite record. So we know that sea level is increasing, and there's some factors, different factors that contribute to this. In 2000, early this year, Frederiksen and all published a paper where they look into these different factors. From the 1900 to 1940, it was mountain glaciers and Greenland ice sheets, the main contributors. During the 70s, there was a decrease in this upward trend due to global dam projects. Basically, there was less water flowing to the ocean from the rivers. And since the satellite era, the main contributors has been the Greenland and Antarctic ice sheets melting, thermal expansion of the oceans, and mountain glaciers melting. So how do we measure this? These different factors, contributing factors. We use tidal gauges around the world, as you can see on the map. We use ground stations. We use satellite data with radar altimetry, gravimetry, and laser measurements. You can see on this map the orbit of Jason 3, which is one of the satellites that measures radar altimetry. So we talk about different factors contributing. The main factors since the satellite record are atmospheric height and ocean mass. So since we have these satellite records, there's been an average rate increase of 3.3 millimeter per year. The atmospheric height contribution is 1.1 millimeters per year, and the ocean mass is 2.1 millimeters per year. I'm going to go and talk a little bit in details of these contributing factors. So the atmospheric height is an indicator for how the change in increasing ocean heat changes the sea surface height over time. So basically is a measure for how the ocean is expanding due to an increase in heat content. You will know this commonly as thermal expansion. As you can see from this time series, it's been steadily increasing the last 20 years or so. How do we measure this? We have gridded temperature and salinity of the oceans up to 2,000 meters with Argo floats. Argo floats are autonomous vehicles that change their buoyancy and profile along the water column, allowing us to have these measurements and other measurements too. You see a couple of pictures of deployments of Argo floats. And on the left-hand side, you see the amount of Argo floats that are actively working in January of this year. This is telling you there's thousands of profiles that allow us to have this specific information. Ocean mass. So ocean mass, and as you can see in this time series, has increased 2.1 millimeters per year. The main contributors are Greenland and Antarctica. As you can see from these images from NASA, we see that in Antarctica, there's areas that there's a decrease of mass of about 1 meter, of ice height of 1 meter, and there's in Antarctica, and there's other areas that there's an increase of this ice height. On the other hand, in Greenland, Greenland coastal areas are basically losing mass constantly. Here we have a time series of Antarctica mass loss and Greenland's mass loss. You can see we have 149 gigatons for Antarctica and 279 gigatons per year for Greenland. And 1 millimeter of sea level equals approximately of 360 tons, or gigatons, sorry, of ice loss. What are the global mean sea level rise projections? So it's likely that sea level is going to rise between 20 to 30 centimeters by 2050. And depending on the global warming scenario, there's going to be an increase of 50 to 7 centimeters for the RCP 4.5 scenario, and the RCP 8.5, there's 40 to 100 meters. Basically, depending on the global warming scenarios that we follow, the measures that we're going to take, we're going to have the level of sea level rise, sea level change. In the most extreme scenarios, you can see here on orange and red, we have up to almost 2.5 meters of sea level rise. So now we're going to look into what the states of the world beaches. Through satellite data, scientists have been able to measure the changes in coastal environments, especially on sandy beaches. From this map, you can see that the changes are not homogeneous around the world, and the changes depend on different reasons. One of the main reasons is sea level rise. 24% of the world's sandy beaches are eroding at rates of 0.5 meter per year. This is a global average. There are some areas that the increase is even higher. And the 28% are accreting, meaning gaining sand, and 48% are stable. The majority of the sandy shorelines in marine protected areas are eroding, so this is a high concern for coastal conservation. So now I'm going to talk about Save the Waves Coalition. Save the Wave Coalitions is an NGO that protects, stewards, and defends surf ecosystems around the globe in coalition with diverse organizations. So its mission is to protect and preserve coastal environments with a focus of surf zones. They achieve these goals through protected areas, economical studies, and direct actions in partnership with local communities. So now I'm going to explain you what surf ecosystem. A surf ecosystem is the coastal environment around a surf break. They have different components. You have the geophysical component, which are the physical attributes, bathymetry, sediment transport, the swell window that allow to have a surfable break. There's the biological component, which are the flora and the fauna, and the socioeconomic components, which is the history of the coastal environment, it's the human history of the coastal environment, the economic activities around it, and these are not necessarily related to surf specifically. The culture around the surf ecosystem, there's increasing surf culture, but there's also they're strongly related with fishing culture. This is one of the places that I'm working with Save the Wave to protect is in Punta Conejo in Oaxaca. That has unique characteristics of a surf ecosystem that we're working really hard to protect against the construction of an industrial port. So how is sea level related to a surfable wave or a surf ecosystem? Sea level rise. On top we have a scenario on which a surfable wave only breaks in a mid-tide condition. There's a specific conditions, geophysical conditions that allow us a surfable wave. And there's been a study by Raymond et al. Where they use local knowledge to look into the danger of the threat of coastal surf ecosystems in California. So basically, there's three scenarios from this study. A natural adaptation in which there's a landward migration of the surf spot with a landward migration of the sandy beach due to sea level rise. So basically, the surf spot moves with sea level rise. It will be the same? We don't know. There's another scenario where natural adaptation is inhibited, in which this landward migration of a surf spot is inhibited by a seawall. Seawalls are the major protections against sea level rise for infrastructures, coastal infrastructures. They're not always works, but that's what it's naturally built. So in this case, the surf ecosystem disappears. And there's this natural adaptation that's impossible due to a cliff that doesn't allow that landward migration of the surf spot. This is a natural adaptation due to sea level rise. So how do we use sea level rise information in Save the Waves? So for Save the Waves, together with the University of Baja California, we've developed a multi-criteria analysis to identify priority areas for surf ecosystem conservation. We proposed a set of indicators to measure the state and pressures on diverse surf ecosystems using GIS systems in Mexico. And we're transferring this methodology all around the world. So how are we going to use sea level rise information? Currently, we're working on including in this multi-criteria analysis sea level rise projections to account for the effects and in surf ecosystems and analyze the threat that sea level rise will have on surf ecosystems. For everyone working in coastal conservation, climate change and sea level rise have become a major concern, and we're working towards mitigating its effects with different strategies. You can see more information in the Save the Wave webpage and in some of our partners like the Surfrider Foundation and Wild Coast. Thank you very much.
Thank you very much, Dr. Pasalakwa. We just heard about sea level rise, and next we'll be moving on to discussing sea ice loss with Dr. Till Wagner. Dr. Wagner is an assistant professor in the Department of Physics and Physical Oceanography at the University of North Carolina, Wilmington. His research focuses on how ice in the polar region grows, moves, and melts. He is also working to understand how changes in the polar regions are connected to the changing climate. To do this, he uses a combination of mathematics, computer models, satellite observations, and measurements collected directly in the polar regions. Dr. Wagner completed his PhD in applied mathematics at the University of Cambridge and spent his postdoc years at Scripps Institution of Oceanography. Thank you very much, Till.
Welcome. My name is Till Wagner. I'm an assistant professor in physical oceanography at the University of North Carolina, Wilmington. And it is my great pleasure to talk to you today about the rapid observed sea ice loss in the Arctic over the last half century or so. Before I start looking at sea ice in detail, I wanted to provide some background about the difference between land ice versus sea ice. So on the left here, we have a map of the southern hemisphere with Antarctica at the center. And on the right, we have a map of the Arctic basin, located at the center of the northern hemisphere. So in the modern day climate, there are two major land ice sheets. An ice sheet is a large body of land ice, and we have the Antarctic ice sheet on the left and the Greenland ice sheet on the right. Now, land ice is formed by falling snow that compresses over hundreds of thousands of years and turns into ice and creates these large bodies of ice. And they can be up to 4 kilometers thick in the modern day climates. Now, the Antarctic continent is surrounded by the Southern Ocean. And in the winter, that ocean freezes over and gets covered by a thin layer of sea ice. So sea ice is just the frozen top of the ocean, and it is much thinner than the land ice. It's typically 1 to 2 meters thick, if that. The same is occurring in the Arctic. The Arctic basin is covered partially all year round in sea ice, and in the winter, the sea ice extends to the peripheral seas as well. So the main point of this slide for me here is that land ice, which sits on land, when that melts, it contributes to sea level rise because you're adding a new volume of water to the existing ocean. Whereas sea ice, on the other hand, is already floating in the ocean. And when sea ice melts, you're not adding any new mass to the ocean. And so sea ice is actually not contributing to sea level rise. So why do we care about sea ice? Well, I'll get back to that in a minute. But first, I wanted to give a little bit more detail on the Arctic sea ice seasonal cycle. So here I have a visualization from the NASA Scientific Visualization Studio. And what we are looking at here is the Arctic sea ice cover as it grows in the winter to extend to low latitudes and then melts back every summer. So in the winter, it grows to up to 16 million square kilometers, and then it shrinks back every summer to something between 6 and 4 million square kilometers. If we plot the area as a function of the day of the year, that's what I've done here, you will see the seasonal cycle. Every curve here corresponds to 1 year. And we've been doing this since the beginning of the satellite era in 1979. So every year we have a maximum sea ice extent at the end of winter in March, and then at the end of summer in mid-September we have a minimum. If I color these curves by the year taken, then you will see a very interesting pattern. The bright beige here is the early years, the earliest being 1979, and the latest one here is 2019. And you can see that over the years, sea ice has become less and less. And this is most pronounced in the September minimum. So I wanted to focus here on the evolution of the September minimum. If we're looking at all these measurements and plot them, the area as a function of the year, you're finding this steady decrease. There's some natural variability between years, which is kind of like the differences in cold winters that we experience and warm winters. But overall, you see that we have started in 1979 with close to 8 million square kilometers of sea ice area in September. And nowadays, we have something closer to 4 million square kilometers. So in 79, the ice cover looked roughly like this in September. And in the summer of 2019, there was only about 60% of this left. So over the last 40 years, we have every year, every decade, lost about 10% of the original ice cover. Now, you might wonder, how accurate are these measurements? And how do we even know all of this? And the broader question is actually, how do we carry out Arctic science? And so that's what I wanted to talk about next. These data that I've just shown you are all collected using satellites. Satellites have become extremely sophisticated and are very good at measuring the areal extent of sea ice. So the data that I've just shown you, we know with a high degree of certainty. Satellites are not as good at measuring the thickness of sea ice. So if we try, for example, to compute the volume of sea ice, our estimates have a much higher uncertainty than for just the area. And also satellites are limited. They don't tell us much about the ocean underneath the ice. They don't tell us really much about the conditions of the ice itself. So we also have a second pillar of Arctic research, which is field observations. We go to the Arctic to take measurements of the ice itself, of the ocean underneath the ice. Here I'm in Fram Strait with some students. We're extracting ice cores to look at salinity of the ice, at ice age, and also at the biology in the ice and underneath the ice. Satellite measurements and field observations are really good for us to study the past and the present of the sea ice. But we also are interested in what the future is going to look like. And for that, scientists develop ice and climate models. These are typically computer simulations that are fed with current data and obey the laws of physics and project out what the sea ice is going to look like over the coming decades, centuries, etc. Now, why do we care? Since I just told you that sea ice is not actually that important for sea level rise, but it nevertheless plays a hugely important role in the climate system. So, first of all, sea ice is very reflective. It is white and it reflects a lot of the incoming solar radiation. You can imagine if you remove the sea ice from the Arctic Ocean and replaced it with open water, it's a little bit like taking a white t-shirt off and putting a black t-shirt on. You're going to absorb a lot more of the incoming heat. And that has far-reaching implications for the local and for the global climate. Sea ice also, when it grows, produces dense water. And that dense water sinks to the bottom of the ocean and helps drive the global ocean circulation. And then one more thing, it obviously keeps the Arctic air temperatures cold as well. So that in itself has important implications for atmospheric dynamics. Beyond the climate system, the Arctic is increasingly receiving attention from humans. And that is because if you remove the sea ice, you are suddenly left with a new open ocean. So here I'm showing a map that was printed in the New York Times a few years ago that shows potential shipping routes between 2015 and 2030 from Europe and North America to Asia. The green routes that you see here are shipping routes where cargo ships could be traveling without the accompaniment of icebreakers. The red shipping routes would still need icebreakers. But up to very recently, it was kind of unthinkable that you would take cargo through the Arctic. But obviously that would be extremely interesting if you didn't have to go the southern routes anymore. Beyond shipping and transport, tourism is increasing, exploding in the Arctic basin. And obviously there is a lot of interest in exploring oil and natural gas extraction in the area, which comes with its own set of promises and risks. And related to that, and in general, very important is the impact of sea ice on the Arctic ecosystem. So, as we all know, the Arctic ecosystem, especially the charismatic megafauna, polar bears and walruses, depend on the sea ice as their natural habitat, as their hunting grounds. But beyond that, the sea ice is also really important, for example, for spring blooms of algae, where the meltwater helps drive these blooms. And the formation of dense bottom water also drives upwelling, which provides nutrient-rich waters from underneath, which in turn also is a crucial component for the Arctic ecosystem. So the sea ice is important, to sum up, for the physics of the climate system, for human interests, and for the local ecosystem. So to finish up with, what can you do about it? What can we all do about sea ice loss and the challenges it presents for the global oceans? And this is always a tricky question, because the Arctic is somewhat of an abstract concept, and the dynamics and sea ice is a phenomenon that are occurring in a very remote place. And so for me, I've always found that learning and teaching about the polar regions and their importance for the global oceans is one of the best ways that we can help raise awareness and protect. So I've chosen to show a picture here of a workshop that I led with middle school girls as part of the Better Education for Women in Science and Engineering program. And I can just encourage all of you to try and learn and teach our next generation of scientists and citizens to appreciate the importance of sea ice in the Arctic and its importance for the global climate system. Thank you very much.
Thank you very much, Dr. Wagner, for that fascinating talk on sea ice loss. For our next session, we will be exploring coral reef loss with Jen McWhorter. Jen McWhorter's PhD between Universities of Queensland and Exeter explores a unique methodology for improving climate projections on coral reef environments. She began her PhD following 8 years of experience in marine spatial planning, ocean observations, and marine policy, most recently from Scripps Institution of Oceanography at the University of California, San Diego. Commonly seen in the literature, downscaling general circulation models over coral reef environments tend to lack important coastal complexities for climate projections. Ms. McWhorter has been developing a unique method for using vertical 1D physical biogeochemical models to drive various 21st century climate change projections over the Great Barrier Reef. By calculating many 1D individual profiles, the model accounts for key drivers of vertical mixing using local bathymetry, tides, and atmospheric inputs, then outputting various column properties such as surface and bottom temperature and photosynthetically active radiation, or PAR. These projections provide a more detailed analysis of frequency and severity of warming events in the future while using relatively simple computing. As a side note, Jen McWhorter was also my TA, the very first GIS class I took in grad school. So thank you very much, Ms. McWhorter, for coming here. And if any of these maps were done poorly, you can blame her, since she taught me everything I know. Thank you very much, Jen.
So thank you for the opportunity to be part of your AGS conference. I'm Jen McWhorter, and I'm currently working on my PhD at the University of Exeter and the University of Queensland under the supervision of Dr. Paul Halloran and Professor Peter Mumby. The focus of my work is on improving the way we model climate projections globally over coral reef environments. And more specifically, I'm focusing on the Great Barrier Reef as a case study. Oddly enough, I first became inspired to study the ocean when visiting the reef in Australia at age 10, and I learned how threatened the reef was to climate change. As you're aware, sea surface temperatures are warming as an effect of global climate change. Corals live near their thermal tolerance, meaning they're extremely sensitive to warming temperatures. Corals can be thought of as part animal and part plant. They have an algal symbiont that lives in their tissue called zooxanthellae, as you can see in the diagram here. This gives them the colors that you see on a healthy reef. When corals become stressed, they expel this algae into the water column and appear white. Their tissue is then transparent, and what you're seeing is their skeleton. At this point, the corals are not dead, and they can actually regain this algal symbiont, but if the warming persists, the stress can lead to mortality. This is what a dead reef looks like, and eventually the structural integrity will break down. On a global scale, 2014 to 2017 was an unprecedented period of successive record hot breaking years, which coincided with the most severe, widespread, and longest lasting coral bleaching event ever recorded. During the 2014 to 2017 warming event, the Great Barrier Reef was greatly impacted. For scale, the Great Barrier Reef is the largest tropical reef system in the world, nearly the size of the entire east coast of the United States. These maps were created using aerial surveys by Professor Terry Hughes and team, and these aerial surveys captured the last 3 mass bleaching events. These events were large scale and resulted in a great loss of coral. The bleaching extended even into portions of the southern Great Barrier Reef in 2020. As you can imagine, recurring years of severe bleaching with little time in between provides less of a window for recovery. So now you might be wondering, what can we expect into the future in terms of magnitude and frequency of severe bleaching events? It is important to know that climate models provide useful information of past and future large-scale climate variability, but they have coarse resolutions and they're unable to resolve certain physical complexities over coral reefs. Before I begin diving into my research, I just want to mention that these results have yet to be published. In order to improve climate modeling, we've developed a method to bring in atmospheric inputs from the climate models over the reef and into the water column. Our technique takes into account the bathymetry details, the locations of corals, things like clouds, pressure, humidity, winds, tides, various mixing properties, and then it simulates a vertical one-dimensional heat transport through the water column. We then repeat this simulation over various points on the reef at our specified resolution and within certain depth constraints. The temperatures throughout the water column at each point will have different properties. After running this vertical simulation on the Great Barrier Reef for various climate models, we now have these results. This figure is showing the magnitude or the intensity of warming in terms of coral stress on the y-axis. This is a commonly derived metric that indicates how long a warm anomaly persists over the reef. When this number reaches 8, it's typically when we see coral bleaching leading to mortality. The different lines on this plot are referencing different future climate scenarios in terms of long-wave radiation or energy that's being emitted from Earth. These climate scenarios take into account various socioeconomic and physical processes that cause changes to our global temperature. The highest climate scenario is indicated in red at 8.5 watts per meter squared. This is also known as the worst case climate scenario, and this refers to global average temperatures reaching near 5 degrees Celsius by 2100. The scenario assumes an energy-intensive fossil fuel-based economy. The next scenario is the 6.0 watts per meter squared, and this refers to roughly 3 degrees of global average temperature warming by 2100. And this lends a pessimistic development trend described as little investment in education or health, a fast-growing population, and more inequalities. The 2.6 watts per meter squared scenario accounts for a significant shift in sustainable practices. And finally, the lowest scenario is the 1.9 watts per meter squared. And this is the preliminary candidate for staying below the 1.5 degrees C of warming by 2100. It considers a decline to zero emissions, followed by a long period of negative CO2 emissions. These climate scenarios can range in variability, which is why I show a number of outcomes. It is thought that we might be headed somewhere between the orange and the blue lines. As you can see in the figure, the 2 low scenarios slightly rise from conditions similar to what we've seen today until about 2048, indicated by the gray vertical line. This is when that lowest scenario peaks. Meanwhile, the high scenarios increase rapidly in the intensity of warming. So those 2 low scenarios remain close to that 8 threshold where we typically experience severe bleaching. Now that I've showed the magnitude of warming projected for the Great Barrier Reef, As I mentioned, it's important to look at the frequency of these events. If there's less time in between warming events, there will be less time for recovery from bleaching. This figure shows the climate scenarios as when they're expected to experience severe bleaching leading to mortality within a decadal window. As you can see, we have a committed warming of 3 to 4 severe bleaching years per decade, even in the best case, lowest scenario of 1.5 degrees C. For context, if you remember earlier, we've just experienced 3 events in the past 5 years on the Great Barrier Reef, which resulted in widespread bleaching and mortality. In contrast from the lowest scenario, the highest scenario is projected to experience severe bleaching events nearly every year by the end of the century, and roughly 7 out of 10 years around mid-century. Coral reefs support fisheries and tourism. They're one of the most biodiverse spots on Earth, and they've been considered the rainforest of the ocean. Coral reefs not only provide food and tourism revenue for coastal communities, they provide protection from storms by creating a physical buffer. Coral reefs also provide an intrinsic value. We simply like knowing that they're there. For the sake of corals, we need to continue on the lowest possible trajectory. As individuals, it may be hard to see how you can make a difference on such global policies. But by making sustainable choices every day, we can all contribute to reducing our impact on the planet. Other things you can do that will really make a big difference are educate and inspire. This is a photo of me when I was 10 years old on the Great Barrier Reef, and the tour operator informing me of the impacts of climate change to corals changed the course of my life. We can also continue to promote equality, such as encouraging young women to pursue science careers. Thank you for your time.
Thank you very much, Jen, for that talk on coral reef loss. For our next topic, we'll be moving to ocean deoxygenation with Dr. Natalia Gallo. Natalia Gallo is a marine ecologist and biological oceanographer currently working as a postdoctoral researcher with the Cal Coffey Long-Term Ecosystem Monitoring Program at the Scripps Institution of Oceanography, UCSD. Her research focuses on climate change impacts on deep sea fish and fishery species. She is also an affiliate of the NOAA Southwest Fisheries Science Center and the Center for Climate Change Impacts and Adaptation at Scripps. She is passionate about the science policy interface using science to inform ocean-based climate mitigation and adaptation actions and has participated in multiple UNFCCC international climate conferences. She is a previous Switzer Environmental Leadership Fellow, National Science Foundation Graduate Research Fellow, and honoree on the Forbes 30 Under 30 Science List, and UCSD TEDx presenter. Thank you very much, Dr. Gallo.
Hello, my name is Natalia Gallo, and I'm a postdoctoral researcher at the Scripps Institution of Oceanography. Today I want to talk to you about why the ocean is losing oxygen and what you can do about it. But first, let's pause and look at this beautiful photograph of a healthy marine ecosystem. Now take a deep inhale. What's happening in your body is that your bloodstream is now carrying new oxygen to all the cells in your body, fueling them and allowing them to perform their essential functions that keep you healthy. But like you, every animal in this photograph is also breathing, though the mechanisms look a bit different from the way in which we breathe. Every fish, coral, and anemone that you see here is extracting a dissolved form of oxygen from the surrounding seawater. And just like us, every animal in this picture has certain oxygen requirements that must be met so that it can be healthy and live in this habitat. Beyond the animals you can see with the naked eye, if we took a drop of seawater and put it under a microscope, we would see millions of microscopic organisms, phytoplankton and bacteria. The vast majority of all of these microscopic organisms also need oxygen to thrive and perform their roles in the ecosystem. As you can see, the ocean is filled with organisms that need oxygen. But what I'm here to talk with you about today is that the ocean is losing oxygen in a process known as ocean deoxygenation. It's a bit of a mouthful, but take a moment to pronounce it with me so that you can feel confident about saying it. Deoxygenation. Ocean deoxygenation. This just means a decline in the oxygen content of oceanic and coastal waters. This decline is primarily driven by eutrophication, which is otherwise known as excessive nutrient inputs into waterways, as well as climate change. In this map, you can see colored in red and blue all areas in the ocean where conditions are already hypoxic. Hypoxic conditions mean that oxygen levels are low enough that they are already stressful to most animals. All of the red sites show coastal hypoxic areas, which have increased rapidly in number and are sometimes referred to as dead zones because they are often associated with mortality events of fish and other hypoxia-sensitive animals. In blue, you can see the regions of the ocean which already have hypoxic conditions at certain depths of the water column. These regions are called oxygen minimum zones and are expanding due to climate change. Ocean deoxygenation can be thought of as an oxygen supply and demand mismatch. Eutrophication and warming from climate change are decreasing the supply of oxygen while increasing the demand for oxygen in the marine environment. On the next slide, we'll talk a little bit more about the actual mechanisms. The ocean is a critical heat sink and has absorbed approximately 93% of the excess heat in our climate system from the burning of fossil fuels. When the ocean warms, however, the oxygen content of the ocean also decreases. This is due to a few factors. First, solubility. Warmer water holds less oxygen, so as ocean temperatures warm around the world, the ocean loses its ability to hold as much oxygen. You can think of this kind of like outgassing of a hot soda. Oxygen also enters the ocean from the air through mixing at the surface of the ocean. As surface waters become warmer with climate change, they become more stratified, thus reducing how much oxygen is actually getting mixed into the water. Ocean warming also leads to changes in the circulation of the ocean. As the ocean becomes more sluggish, deeper waters are supplied with less oxygen. Meanwhile, as temperatures warm, oxygen demand by marine organisms and bacteria increases. In coastal areas, these warming-driven changes in oxygen are further exacerbated by excess nutrients that enter waterways, causing algal blooms that lead to low oxygen events as they decompose. Together, solubility changes, decreased mixing, changes in circulation, increased respiration, and excess nutrients all contribute to the loss of oxygen in the global ocean and coastal zones. Ocean deoxygenation is a topic that has only recently received a lot of attention. When I first started out with my PhD at Scripps, very few people who I spoke with had even heard about ocean deoxygenation. This cartoon from Baz Kohler captures well my experience speaking about ocean deoxygenation to the public and to policymakers. Here, the fish are fleeing due to deoxygenation, but the customs official says he has never heard of that nation. The last few years have seen a huge expansion in the research on ocean deoxygenation, as well as compilations of knowledge from scientists. Just last year, the International Union for Conservation of Nature published a giant report bringing together the state of the science on ocean deoxygenation. Ocean deoxygenation is now a very active area of research, and scientists all around the world are working to understand how much oxygen loss has already occurred, what the ecosystem impacts of oxygen loss are, how much oxygen loss is projected for the future under different climate scenarios, and how oxygen loss interacts with other ocean stressors that you've been hearing about today. Briefly, what we already know is that ocean oxygen loss is a substantial problem. Using long-term measurements of ocean oxygen taken from all around the world, scientists have found that since approximately 1950, the ocean has lost about 2% of its oxygen. In the figure on the left, in red, you can see all of the areas where oxygen loss has occurred, and areas in darker red have experienced larger losses than the global mean. Climate models project more rapid oxygen loss in this century, and by 2100, global oxygen levels are expected to decrease on average by 3 to 4%. In the figure on the right, you can see climate model projections for oxygen loss for the most recent climate model comparison. Oxygen declines throughout the 21st century, but less oxygen loss occurs under the most ambitious climate policy scenarios, which you can see here in the purple and the blue lines, compared to the business as usual scenario, which you can see with the red line. While 3 to 4% decrease may not seem so large, small changes in oxygen matter, and certain regions experience much greater oxygen losses. In coastal areas, these climate-driven losses of oxygen are further exacerbated by increased microbial demand for oxygen due to the influx of increased nutrients and organic matter. Since nearly every organism in the ocean needs oxygen, oxygen plays a key role in structuring marine ecosystems and affects where species can live. For example, species that are very active and have high metabolic requirements, such as tuna, can only live in well-oxygenated habitats. Other species, such as this marine worm here, have evolved special adaptations that allow them to live in hypoxic environments. For this reason, hypoxic areas are not dead zones because certain hypoxia-tolerant species can thrive in these areas. However, mortality events of hypoxia-sensitive species, such as the crabs and the fish pictured here, often occur when coastal regions experience hypoxia. The ecosystem and societal implications of ocean deoxygenation are changes in species distributions, food web changes, decreased biodiversity, impacts to fisheries, and also potential climate feedbacks. Nitrous oxide, which is a potent greenhouse gas, is actually produced in low oxygen regions of the ocean when microbes use nitrate and nitrite instead of oxygen to breathe. As I mentioned before, the field of research around ocean deoxygenation is rapidly growing. My own research has examined how oxygen structures deep-sea fish communities and explored some hypoxic superstars, animals such as this cusk eel and cat shark that are LIGO-oxyphiles, or low oxygen specialists, and can thrive under oxygen conditions that are lethal to most fish. I have also used new tools such as deep-sea landers and worked with long-term data sets like the Calcoffee Ecosystem Monitoring Program to study species vulnerability to oxygen loss across both short and long time scales. This research contributes to understanding of the ecosystem and fisheries impacts of oxygen loss and how we can best manage these changes. I hope that you've enjoyed this presentation, but I also hope that you are listening with the intent not just to learn, but also a drive to do something. So here are a few things you can do. First, be informed and share your knowledge about ocean deoxygenation. There are a few excellent new resources, such as from the UNESCO GONE group and the IUCN Ocean Deoxygenation Report that I highly recommend. Second, look for personal changes you can make to decrease your own contributions to ocean deoxygenation. These include transitioning away from fertilizer-hungry lawns, calculating and lowering your carbon footprint, and making purchasing choices that support more sustainable food production practices. But personal choices only get us so far. Sound and ambitious climate and watershed management policies are necessary to prevent and manage further ocean deoxygenation. Be active and demand ambitious policies from your representatives at the local, state, national, and international levels. Thank you for your interest and your attention, and I hope you feel empowered to make a difference.
Thank you very much for that discussion on ocean deoxygenation, Dr. Gallo. Next, we'll be hearing from Dr. Matthew Costa, who will be discussing mangrove deforestation. Dr. Costa is a postdoctoral scholar in the Center for Climate Change, Impacts, and Adaptation at Scripps Institution of Oceanography. He completed his doctoral research at Scripps on sediment carbon stocks in mangrove forests across northern neotropics, conducting sampling across Panama, the Galapagos Archipelago, and Mexico. He completed his postdoctoral dissertation, Mangroves in Depth, Long-Term Carbon Burial Across Spatial Scales, in 2019. Prior to study at Scripps, Dr. Costa researched coral reef and mangrove ecology at the Bermuda Institution of Oceanography, or of Ocean Sciences, as an undergraduate in ecology and evolutionary biology at Princeton University, completing a bachelor's thesis on mangrove species donation in 2011. Dr. Costa's current work focuses on coastal blue carbon and flows among coastal ecosystems in La Jolla and sequestration of carbon in protected and restored wetlands in San Diego. Thank you very much, Dr. Costa.
Hello, my name is Matthew Costa. I'm a postdoctoral scholar at the Center for Climate Change Impacts and Adaptation at Scripps Institution of Oceanography, University of California, San Diego. And today I'll be talking to you about the global issue of mangrove deforestation. So what this globe represents is the global distribution in purple or pink on the subtropical and tropical coasts around the world. So first I'll discuss what are mangroves, and then we'll
talk about what is their global status around the world. So mangrove is a swamp. That is a type of wetland that's dominated by trees, and specifically a type of swamp that lives in salty environments, so the marine coastal environment. The different mangrove species are found in different, what we call intertidal zones, so different locations in the intertidal zone. The red mangroves, as you can see here, with their prop roots, help them live in the low intertidal, closer to the ocean, whereas other species live higher up in the intertidal zone, such as the black mangrove, whose above ground root structure is called pneumatophores. You can see here, these are found higher up in the intertidal zone. Not just the trees have this sort of intertidal zonation, but the creatures that live on all of these roots show this zonation as well. So the roots of mangroves create a habitat for an amazing and beautiful diversity of encrusting invertebrates, algae, and microorganisms. And these organisms also are zoned in the intertidal on their root habitats, which is really amazing. So even though there are only a few different mangrove species of trees in any given location, the abundance and diversity of other organisms is incredibly high. So we have encrusting invertebrates and algae on the roots, scavenging and predatory crabs, also predators from the air, such as birds from land and ocean, as well as a diversity of juvenile fish and other marine organisms that use the mangroves as nursery habitats. All of these different kinds of diversity, as well as many, many microorganisms you're just beginning to understand, are housed in the mangrove ecosystem. Unfortunately, these incredible and diverse ecosystems are being lost rapidly around the world. This time lapse shows over 30 years the replacement of mangrove and coastal forest ecosystems in Quintana Roo, Mexico. So what do we know about this loss of mangrove ecosystems around the world? It's been estimated that by the end of the 20th century, more than 35% of mangrove area was lost globally. During the late 20th century, these rates of mangrove loss were observed to be highest in the Americas, actually reaching rates of up to 2% of global mangrove area lost per year. And where one of the major risks, and especially in the Americas, in some places, were the conversion to shrimp pond aquaculture, as you can see in this picture. Today, it's estimated that about 137,000 square kilometers of mangrove remains around the world. And in the last 20 years, since 2000, the shifts in global deforestation trends there's been a shift that's occurred toward Southeast Asia. So if you look at this graph, where Southeast Asia has the most red, not only in total mangrove loss in hectares, and that's partly because there's just so much mangrove area in Southeast Asia, but also mangrove loss as a percentage of original area. As you can see here, in both cases, you have a lot of red in this part of the world, showing highest rates of mangrove loss in Southeast Asia. This graph gives you a better idea of what are the drivers locally and regionally in mangrove loss in different parts of the world since 2000, where we have, there's a lot of information here. So these squiggly lines at the top and at the side represent the longitudinal and latitudinal distribution of mangrove deforestation around the world. What I'd really like you to focus on is these colored squares on the map. So the colored squares represent sort of mangrove cover around the world, and the color of the squares represent the major cause, the major driver of mangrove deforestation in that region, where red squares represent replacement of mangroves for settlement, orange represents the replacement due to production of commodities, such as for agriculture or aquaculture, so fish farms, shrimp ponds, etc. Non-productive conversion represents the loss, and that's yellow, represents the loss of mangroves unintentionally due to land use changes perhaps somewhere else, as we'll discuss later. Green represents extreme weather events, such as major storms, and blue represents the loss of mangroves due to erosion. And these sort of big squares at the bottom summarize what the major drivers of mangrove loss are in different regions of the world. So C and D, these are North and South America. Here and in Oceania, you have dominating are the causes of extreme weather events and erosion. Whereas in Africa, non-productive conversion plays a bigger role, and in Southeast Asia, which again is the hotspot of mangrove area overall and also of mangrove loss, is dominated by conversion to commodities, especially today, palm oil plantations. So it's easy to imagine how conversion to a plantation or settlements could damage wetlands, such as mangroves, but also it's possible for, in the case of the yellow non-productive conversion, decisions that happen many miles away can really negatively impact mangroves on the coast. And a clear example of that is this study by some of my colleagues, Excura et al. In Mexico, where they showed that we have 4 rivers here that go into the Pacific Ocean. These top and the bottom ones have hydroelectric dams many miles upstream, which as an unintended consequence prevent a lot of sediment from reaching the coast. And as we see in this column here is showing in red the area that is lost mangroves from the delta on the coast over several years, whereas in these dammed rivers, whereas the undammed rivers have stable coastlines. So this is an example of how these sort of non-productive conversion of mangroves can be a really big problem in coastal areas. In addition, even the loss of mangroves due to extreme weather events and erosion are related to human activities, because extreme weather events are increasing in intensity due to climate change. And this is an area of mangrove dieback in Baja California, where wave and weather events have killed the fringe or the edge of the mangrove environment, and so they've died back. So these extreme weather events are increasing due to climate change, and also sea level rise is accelerating due to climate change, and as a result, mangroves that are experiencing erosion are further challenged by rising sea levels. So, why, you might be asking yourself, why should I care about these mangroves and maybe in places in part of the world that I don't even live in? Well, I think that these ecosystems are valuable in their own right, but if you need more convincing than that, there's actually something in it for us. Mangroves produce lots of what we call ecosystem services. So these are processes that are carried on by ecosystems that provide economic value to humans, and they do it for free. Mangroves support fisheries species, so species that we catch and sell and eat. They improve water quality. They foster lots of other valuable biodiversity. They counteract erosion by depositing sediment, and they protect coastal areas from the impacts of storms, saving lives and property. And they sequester carbon, which is my special area focus on my research. So really interesting that mangroves are both threatened by climate change, but they're also one of our best allies in fighting climate change, as we'll discuss. So here, very quickly, I'll show you some carbon sequestration data in different ecosystems, where we have a logarithmic scale on the y-axis, so that's really important to notice, of carbon burial and grams of carbon per unit area per year. And what this shows is that these ecosystems, what we call blue carbon ecosystems of salt marshes, mangroves, and seagrass beds, sequester about 100 times more carbon, or sequester carbon 100 times faster than these terrestrial forests. And that's because these ecosystems have sediments that are accumulating and that really help bury the organic matter and preserve it in the ground maybe for thousands of years. So these are really effective carbon sinks. So in light of climate change, destroying these ecosystems is really the last thing we should be doing, and yet that's what's happening around the world. So the good news is that it seems that mangrove deforestation rates have been slowing down in recent years. And so if you want to contribute to positive movement in this direction, what can you do about it? Locally, you can support restoring coastal ecosystems, either with volunteering, getting out there yourself, restoring ecosystems, and promoting their use as sort of the green infrastructure that they are for coastal adaptation and resilience. And even if you don't live near mangroves, as I do, you can get into your local coastal ecosystem or other ecosystem, such as, for me, that's the salt marshes in Mission Bay, to help protect them and support their ecosystem services. So even if you live someplace without mangroves, you have something you can contribute to. globally, there are lots of things you could do to reduce your ocean impact on ocean ecosystems, including reducing your carbon footprint, which again, climate change is impacting these ecosystems around the world. Reducing your plastic pollution can help make sites like this of really plastic impacted growth forests less common. And you can be an informed consumer, being careful not to consume goods that were made by destroying mangroves or other forests. But I'd like to end on a positive note. So look at this graph, which shows the top 15 countries ranked by their mangrove area around the world. And one hopeful piece of information from this is that 50% of the world's mangrove area, so if you see it goes down to here, is in just 6 countries. And 75% of global mangrove area is contained in just 15 countries. So what that means is that if just a few countries set really ambitious goals for protecting coastal environments and using them for climate change mitigation, the global mangrove deforestation problem would be essentially solved. And so what this requires is international support and pressure. And we have there's a process for this, which is through the United Nations called the Paris Climate Agreement. And that's why it's so important that the president-elect has announced that the United States will rejoin the Paris Climate Agreement. And we have to keep calling on our elected officials to, regain American leadership in this sort of international push to fight climate change, including by protecting these ecosystems, which can be our best natural allies in fighting climate change. So with that, I'd just like to say thank you for listening.
Thank you very much, Dr. Costa. Mangrove deforestation has always been one of my favorite subjects in this session because I knew so little about it. Thank you very much for illuminating that topic for all of us today. Next, we'll be hearing about a topic that is near and dear to my heart as well, ocean plastics, with Dr. Jennifer Brandon. Dr. Brandon received her PhD in biological oceanography at Scripps Institution of Oceanography in 2017, focusing on nascent field and marine microplastics. She is an expert in quantifying and identifying marine microplastics and has developed multiple novel methods to identify the smallest sizes of microplastics and determine the age of plastics exposed to varying weather conditions in the environment. She was the first to find temporal trends of microplastics in the sediment record, and the exponential increase of microplastics she recorded from 1945 to 2009 closely correlates with exponential increase in worldwide plastic production over the same time period. She also has an extensive knowledge in marine ecology, having spent much of her PhD doing lab and field work on the California current ecosystem, plankton ecology, and how microplastics affect the bottom of our food web in that region. Dr. Brandon is highly accomplished in the world of scientific communication, having given hundreds of interviews and lectures to all types of stakeholders, and recently completed her tenure as a Price postdoctoral fellow in science communications at the Birch Aquarium at Scripps Institution of Oceanography, where among her other duties, she taught graduate and undergraduate courses in communicating science to the public. She has been interviewed by BBC, NPR, The Guardian, and the Los Angeles Times, among many other organizations. Thank you very much, Dr. Brandon, for joining us today.
Hi, my name is Dr. Jennifer Brandon. I'm a biological oceanographer who studies plastic pollution in the ocean. As you can see from this globe, ocean plastics are a worldwide problem. We find them around the ocean, but especially concentrated in the 5 subtropical gyres. So in this diagram, you'll see the pink areas that are concentrated in the middle of the ocean. Those are the subtropical gyres where the plastic concentration is the most dense on the surface ocean. I'm going to talk a little bit about how the plastic gets there and why it's so concentrated there. So ocean pollution is a relatively new problem. Plastic is only about 100 years old as a substance. It was invented in 1907, but we didn't widely use it until World War II and right after World War II. But since then, we have had an exponential growth in global plastic production, and we are currently up to approximately 407 million tons of plastic produced annually worldwide. And of that 407 million tons, approximately 4.8 to 12.7 million metric tons enter the ocean annually. That plastic gets into the ocean from polluted rivers and harbors, like these 2 bottom pictures show you. Those rivers flow into the ocean. Dirty harbors drop it into the ocean off of ships. And that flows through currents into the subtropical gyres, where it gets stuck, sometimes indefinitely. And there is an estimated standing stock of 5.25 trillion pieces of plastic floating on the ocean's surface. But that's just what's floating on the surface of the ocean. What's sunk to the bottom of the ocean is actually vastly understudied. And so we are really just kind of at the beginning of studying how much plastic is currently in the ocean. What you think of when you think of plastic in the ocean is often those last pictures of really polluted rivers, large pieces of plastic, or this top image on the right of a really big thing of nets, large tires floating in the ocean, animals entangled in plastic. But that's actually not what most of the plastic in the ocean looks like. Over 90% of the plastic in the ocean is microplastic, or plastic that's smaller than 5 millimeters. So in our lab at Scripps Institution of Oceanography, we counted over 32,000 pieces of plastic from the Pacific subtropical gyre, and we found that over 90% of them were smaller than 5 millimeters. To give you a reference of how big 5 millimeters is, that's half the size of an M&M. So this is really, really small plastic. I then went and looked at even smaller plastic than that had kind of been missed in earlier studies, and I found that we were actually underestimating how much plastic is in the ocean by an order of magnitude of 5 to 7 orders of magnitude of plastic. So the plastic in the ocean is tiny. It's the vast majority of it by number is tiny, little minuscule microscopic pieces. These pieces can be fragments that are from larger things that have broken down. They can be from fibers that are coming off of ropes. They're coming off of our clothing, and they're getting into the ocean. They can be from microbeads that are manufactured to be that small, or they can be from nurdles, which are pre-production pellets that are made to be that small. The reason that microplastics are the issue in the ocean when it comes to plastic pollution is that they can enter every layer of the food web. They can be eaten by really tiny things like plankton, which are the base of the oceanic food web, all the way up to something like a blue whale that filters vast amounts of water and are eating microplastics as well. And microplastics have the potential to bioaccumulate in tissue. So they're small enough that they can actually enter into the muscle tissue of animals and then be eaten and bioaccumulate up that way. We've started to find them in pretty much every environment we look for them in. So we're finding them in sea ice, we're finding them in rivers, we're finding them in oceanic sediment. We've begun to find them traveling around in the atmosphere because they're so small and buoyant. And we've even begun to find them in inland soil. So this is no longer just an oceanic problem. And we are also finding them in human food sources as well. So we depend on the ocean for many things, including seafood, sea salt, and our own drinking water can come from desalination plants. But also fresh water is now contaminated with microplastics. So we're beginning to see microplastics in our daily lives. So the implications of this are manifold. I did a study where we looked at microplastics in oceanic sediment. And this top graph shows that we found sediment plastic deposition at basically the same rate as that graph I showed you on the first slide of world plastic production. So if you see that these two graphs have basically the same slope, that shows that we are leaving plastic in our marine sediment at the same rate as world plastic production, meaning we are leaving plastic behind in what is going to become our fossil record. So as you think about the Bronze Age or the Gold Age or the Iron Age that you learned about back in history class, we have the potential to be known as the Plastic Age in future history, because that is what we are leaving behind in our fossil record, which I would not say single-use plastic is maybe our greatest invention, but it is what we are leaving behind. Humans are consuming plastic. We now know enough to say definitively that we are consuming plastic. Some studies say that we eat about 5 grams of plastic a week, which is approximately the same size as a credit card. That is a lot of plastic. The health effects of that are unknown, but we do know that plastic has harmful additives and chemicals in it. And we know that we are harming animals with this plastic. So we know that 1 in 3 species of marine mammals have been entangled in marine litter. Every other sea turtle that is out in the ocean, so 52% of sea turtles out in the ocean have consumed marine plastic. 86% of sea turtle species have consumed plastic, as well as many seabird species. So we're harming animals that we care about that are endangered, as well as animals that we depend on for seafood. So what can we do about this problem? The great thing about ocean plastic is that this is a consumer-driven problem and a relatively new problem. We got into this problem in about 50 years, so we can probably turn it around in about the same amount of time. And because it's a consumer-driven problem, there's a lot of consumer-driven solutions. So probably the easiest one that you've probably heard about is bringing reusable cups, bottles, straws, and bags everywhere you go, and refusing things like coffee lids and straws when you have forgotten your reusables. You can also buy in bulk. So when you're at the grocery store, not buying everything plastic lined, but actually buying things in bulk can really reduce your plastic footprint. You can buy non-plastic reusable alternatives to many everyday items. You can participate in beach cleanups, especially if you live on the coast. But if you don't live on the coast, you can clean your local lakes and rivers. And pretty much all of those rivers will eventually end up in an ocean. So that plastic will eventually get out into my samples. So we appreciate it. And you can get involved in banning single-use plastics in your community. So there are a lot of organizations that are involved in the activism side of this that are working to ban things like single-use styrofoam packaging, banning plastic bags, banning microplastic, microbeads in products. So if the activism side of it is kind of more interesting to you, there's a lot of organizations that are doing that on a city-by-city basis. And with that, that is just a brief overview of ocean plastic pollution. And there's much more to say, obviously, but that's kind of the beginning of the talk.
Thank you very much, Dr. Brandon. I especially appreciated your insights into what the average person can do about ocean plastics. Ocean plastics has always struck me as a particularly upsetting problem because it does seem so preventable. So thank you very much for illuminating that for all of us. The next topic we'll be exploring today is one that is equally interesting to me and also equally preventable. It's ocean ambient noise pollution, and we'll be hearing about this from Dr. Kevin Heaney. Dr. Heaney has spent his scientific career exploring the interaction of the ocean environment and acoustic propagation. Some interesting questions addressed include three-dimensional propagation of low-frequency sound across ocean basin and its diffracting behind islands and seamounts, modeling the impacts of ocean waves on multistatic anti-submarine warfare, calculating how far away we can hear fin whales, and parameterizing the ocean soundscape in the presence of anthropogenic noise. After receiving his PhD in applied ocean sciences from Scripps Institution of Oceanography, Dr. Heaney has worked for a variety of companies, from SAIC and Lockheed to more recently Oasis, and had the opportunity to be mentored by many of the great minds from the previous generation, including Dr. Cooperman, Dr. Cox, Dr. Bagro, and Dr. Monk. He has the most fun when he's doing solid science and is able to package that into a system that people, like sailors and managers, find useful. Starting his company, Applied Ocean Sciences, in January of 2019 is a major step forward in combining his passions for solving challenging science problems and getting these solutions into the hands of people who will use them to do good things. On a side note, Dr. Heaney is also my boss, so be nice. Thank you very much, Kevin, for joining us today.
Thank you, Chris, for that introduction. I'm Dr. Kevin Heaney from Applied Ocean Sciences, here to talk about ocean noise and underwater ocean acoustics. I'm super excited to be at Geography 2050. It's my first foray into this community. But one of the things I like the best about ocean acoustics is how global it is and all of the geography that I get to play with. So I'll be talking about the global ocean challenges. The one in particular I'll be addressing is ocean noise. And so here's a we have to start with a globe if we're doing geography. This is a global shipping model, which I'll show you later in real detail, but it just shows you the average sound level for the month of April, over the ocean. This is only shipping; it doesn't include wind. So if you look in the southern ocean here, we're in the South Pacific. You can see that it's very quiet. That's a region dominated by wind. But you can see shipping lanes. You can see in the polar regions it's noisy. it's shallow other places. So the outline of the talk, I'll be talking about sound sources in the ocean, sound propagation in the ocean, marine mammal presence and sensitivity. And I'll be going through a global ocean model that we have, look at COVID-19 impacts. We'll talk about the Arctic. These are, so certainly places where there's rising concern about the impact of man-made noise. So first, a bit of background. Sound travels very well in the sea, which is why marine mammals have evolved with the capabilities of listening and sending sound. Here's a plot showing levels and frequency on the x-axis. So very low frequencies are on the left with 10 and 100 hertz. That's what we hear, up into the 1,000 hertz and 10,000 hertz. This is where the dolphins transmit sound. These blue lines are wind noise for high wind speeds, and you can see they peak around 500 hertz. And the red and orange here are shipping noise in the lower frequencies, and then very loud things are earthquakes, which are louder than everything else, but they're very low frequency. I recommend the docits.org website it's this discovery of sound in the sea for really great background information on all of this stuff. So sound in the ocean doesn't travel straight. It goes up and down depending on the temperature profile and pressure. You can see on the left, if there's a surface ship, sound goes down right away, and then it bounces off the bottom, and you end up with these refracted paths in deep water. If you're in northern latitudes, the sound speed has a minimum near the surface, and you end up with the sound being trapped near the surface, and sound travels significantly better. You'll see evidence of that in our global sound maps. In shallow water, there's no refraction. Sound just hits the surface and the bottom, and it dies out with range. This is a plot in the Barents Sea. So depending on where you are geographically, the sound can travel in very different ways, and that'll affect the average sound. We anticipate, in the low frequencies, sound will travel all the way across the ocean. So animals and ships are hearing each other from quite a significant distance. So the sound sources in the ocean, the natural sound sources are wind and waves. We think of them together. The wind blows and the waves form, and then the waves break and bubbles make noise. It's a combination of all of the above, depending on your frequency. Rain makes noise, and marine mammals make a significant amount of noise, or an observable amount of noise. And then lightning is super loud. I didn't add earthquakes and volcanoes. They're also in there as well. Anthropogenic or man-made sound sources are shipping, seismic exploration, where they're setting off shots, or impulsive sounds to study the seafloor and below it, looking for oil. Those can be heard all the way across the ocean basin. Navy sonars of multiple types. Pile driving in shallow water is important. And then explosions. There's lots of unexploded ordnance in the world, and if it's detonated, it makes a significant sound that can be heard a long ways. In particular, the North Sea between the UK and Europe, there's a significant problem of unexploded ordnances, and it affects the ocean soundscape there. So marine mammals and sound. So, marine mammals, and not just mammals, but fish and invertebrates, they use sound for hunting, for communicating, and for navigating. How much so, we're not quite sure, but they do hear each other and talk to each other. And we have recordings of them grunting and using sound while fishing, in particular dolphins. There's a study, this is getting towards the health of the animals in the ocean soundscape. On September 11th, the shipping numbers in the world dropped because of an immediate freeze of the terrorist attacks on global security. But there's a paper put out in the Bay of Fundy, which is eastern Canada. It went from 12 ships in the small bay, which is a loud area, down to 3 ships, and it reduced the shipping noise level by 7 decibels. So that's a number to keep in mind. That's a large number. 3 dB, or 3 decibels, is twice the amount of energy. And so dropping it by 7 is significant. It turns out to be a fourth. But at the same time, these researchers were doing studies, and they have hormonal measurements from fin whales. They picked up the feces using fishes and nets and feces-smelling dogs, and then studied that and observed a significant drop in the cortisol level, which is a stress hormone. So the animals are in the noisy environment, but the presence of shipping and the increase in shipping is certainly raising, there's observations that it's raising their stress level. So that's one of the reasons we care. The other is limiting their communication distances and their ability to hunt and navigate, which are hard to quantify. So let's talk about modeling ocean noise. Actually, these might be slightly in the wrong order, but I'm going to show you a impact of COVID, where there's also a significant drop in the numbers of ships due to reduced economic activity. Spire provided the AIS data. AIS is a global positioning beacon for each ship, and we have the March, April for 2019 and 2020. The acoustic model was run from every source out at 50 hertz, and then we've molded them together to get the ocean soundscape. So we're going to start with April 2019. This is a snapshot, so every dot you hear is an individual ship. We've run from the ships out, and let me use the mouse and show you some things. One of the things you see is that, again, it's super quiet in the South Pacific. This is shipping only, so there's no wind on this. And then when you get further into the northern latitudes, there's a lot more ships because of the US-Asia connection and the US-European and Europe through the Med to Asia. And so but the other thing that happens is the polar surface temperatures are significantly colder because of the climate and the distance from the equator, and sound travels better in those regions. It stays off of the seafloor. So part of what you're seeing here is a large number of ships, but another part you're seeing is significant propagation effects. In the South Pacific, there's very poor propagation. You can see that here. If we go to the average of the month, this is the entire month of April average for 2019, now you start to see shipping lanes. There's several lanes from the Cape of Good Hope up to Brazil, across to Buenos Aires, and then south. You can see a shipping lane here along South America. In Europe, there's a really nice shipping lane here from Cape of Good Hope up to the Strait of Malacca. You also see very high shipping levels in the Bay of Biscay, off of France and Spain, as well as the Med. And there's lots of traffic going to Russia along the coast of Norway. So this was done for the April 2019 time period. And then the next plot is the April 2020, which is after COVID. There's one anomaly which will catch your eye, which is right here. There's a ship that sat there the whole time. It's probably not real, but it wasn't filtered out. Apart from that, you can see that the lanes narrow, and there's significantly more blue and black between the two. If I go back and forth, if you take a spot and focus your eye on it, you know, from 2019 to 2020, there's an observable drop in the noise level across the board. I should also point out that the dynamic scale here is in decibels per micropascal squared, but it's 50 dB of dynamic range. So the dynamic range is huge. If you're seeing anything, it's a notable drop. I'll point out a couple places. One, there's a lot less ships going around the Cape of Good Hope. Strait of Magellan from the Good Hope. There's a region. And anyway, so if we do a difference map, we see, and this is now plotted of every place with color. This is the difference, the reduction in sound due to the lack of shipping and COVID. And so one of the things you see is it's kind of dominated down off of Antarctica, where there are very few ships, and so that's not particularly relevant. What is important is, you know, the wide swaths of area where here in the central North Atlantic it's significantly quieter. It's a lot quieter north of Halifax and Nova Scotia, and this is the European-US shipping lane. North of Hawaii, there's a large region that is quieter. South of Australia, it's significantly quieter. This is the difference between April 2019 and April 2020. So the global average on this was about 3 dB, which is, you know, again, is a doubling. So there's a between 2019 and 2020, there's a halving of the acoustic energy in the global ocean. And so what that means, though, is that if you're a marine mammal and you can hear another marine mammal at 20 kilometers, if you reduce the level by half, that would allow you to hear another animal at twice the distance. So instead of 20 kilometers, it's now 40 kilometers. And that can have significant biological impacts. So here's a couple line plots from a few places in the Atlantic. The black is March 2019. Blue is, black is March 2020. Blue is April 2020. Red and yellow are March and April of 2019. And so this is the Bay of Biscay. You see in April, there's an observable difference in April compared to March as things really ramped up. But this is the Bay of Biscay, the Western Mediterranean. the North Sea near Norway, and then the central North Atlantic. So, 3 to 5 dB or 2 to 5 dB average increase or decrease in the sound level. There's a few spots in the Pacific, particularly north of Hawaii. There's a very large signal. We're not quite sure why. Other places there are not big signals. Some of these were because of a small sample size and a movement of the shipping lanes. So let's move on to the shipping noise in the Arctic, which is a big issue. The Arctic Council through PAIM and the World Wildlife Fund have funded a study to look at shipping noise levels between 2013 and 2019 and the impact of the reduced sea ice due to climate change. And so we've been modeling this. We just started. The results will be hopefully presented to the Arctic Council in January or February. So the shipping noise will be modeled from 20 hertz, which is the frequency of fin whale and blue whale transmissions, all the way up to 10 kilohertz, which is where narwhals and dolphins communicate. So the plot on the left is the AIS data from just a snapshot of the data or actually an year average of the data from PAIM. It's the Arctic shipping data. It's the Arctic ship traffic data set. We'll be using that to say where our ships are. It's been filtered, and we're looking primarily north of Iceland in the Bering Sea, Barents, and et cetera. So here's a sound map of sound for the first week of September in 2019. If you follow the map, this is the ice line. It's not a minimum year, but it's significantly down. And we've studied basically the Barents Sea, the Davis Strait, and the Northwest Passage. This is the Beaufort and Chukchi, and then this is the Bering Sea. And so lots of traffic around Norway up here, through the Russian coast, along the Russian coast, and then a lot of traffic, a lot meaning 4 or 5 ships in 1 week through the Bering Strait. And you can see that over here. The model is run on, and that's what the little dots are for. But everywhere you see, there's a significant rise in the noise level over ambient sound. Here's the traffic lanes through the Bering Strait. These are Russian ships, and these are American, presumably. And it's much louder in the western Bering Sea, where it's deep water off of these Russian ports. This is where the marine mammals are, in the shallow water on the shelf, and sound doesn't travel very well there. So if we look at a couple blow-ups, the left is the Bering, Beaufort, and Chukchi. It's the same model. Here's the deep water. You can see the propagation. 90 dB, 87 dB average sound level. That's 30 dB above wind noise. And then up here you can see that the deep water in the Beaufort has an increased level. In the shallow water, ships need to be pretty close to you for marine mammals to hear them. In the Northwest Passage, now you see ships going through really constrained waterways. It's significantly noisy there. This is Davis Strait and Baffin Bay, and this is a lot of servicing of the Mons and the population in Greenland. So we're doing this work for the 6 years, for all seasons. There are about 600 ships in the Arctic in September. That number drops significantly when the ice in midwinter. So to conclude, the ocean is a noisy place. Animals have used this for group communication, food localization, and navigation. Some of that we observe and can define quantitatively, others we postulate. Man-made sounds are a significant portion of the ocean soundscape, and it likely increases the stress, and it severely limits the animal's ability to use sound. This is called masking, when they can't do what they want to do, they can't hear as they need to due to increased man-made sounds. And again, as climate change increases and it induces Arctic sea ice melting, this will open up the Northwest Passage for more months and more seasons, possibly all year round, and the sensitive ecosystem in the Arctic could be at risk due to shipping noise. So thank you for your attention, and that's it.
Thank you very much, Dr. Heaney, for that discussion on ocean noise. It's always been interesting to me that we don't normally think of noise as a pollutant, but it really is. It is something that we as people put into the environment that is harmful for the environment and the organisms that live there. So thank you very much for that discussion, Dr. Heaney. For our next topic, we'll be discussing overfishing. with another renowned expert in this field, Dr. Karina Marakovich. On a personal note, Dr. Marakovich was actually my undergraduate academic advisor at the U.S. Coast Guard Academy way back in the day. Now, Dr. Marakovich is currently a professor at the Coast Guard Academy, where she teaches fisheries biology, fisheries management, and atmospherics and marine science. She is the chair of the Education Committee for the Southern New England chapter of the American Fisheries Society and a faculty fellow for the Goodwin Nearing Center for the Environment at Connecticut College. Karina has an MS and PhD in fisheries science from Oregon State University. Go Beavers. She was born and grew up in Sao Paulo, Brazil, and studied oceanography at the Universidade do Estado do Rio de Janeiro. Her research draws from fisheries and environmental sciences, maritime security, and scholarship of teaching and learning. Thank you very much for joining us today, Dr. Marakovich.
My name is Karina Lawrence Marakovich. I'm a professor of marine sciences at the U.S. Coast Guard Academy. One of the areas of concern for ocean conservation is overfishing. On this globe, you can see that based on Global Fishing Watch data, commercial fishing is concentrated on the coast of many countries where upwelling brings rich nutrient waters to the surface, which combined with nutrients from terrestrial runoff allow for high primary productivity. Another area of high fishing pressure is around the equator, where equatorial upwelling also allows for high productivity. Currently, the Food and Agriculture Organization, FAO, of the United Nations, it estimates that 60% of the world fisheries are fully fished, and the latest data shows that at least 33% of the fisheries are actually overfished. So also looking at the globe and the data reported by the International Maritime Bureau, we note that there is a high incidence of maritime crime in Southeast Asia, the Arabian Peninsula, as well as the East and West African coasts, and most recent information of maritime crime in South America as well. The same areas where we also see a lot of fishing pressure. The problem is three-pronged: weak maritime governance, leading to overfishing, which in turn can increase maritime crime. Weak maritime governance means that countries may not have enough laws and law enforcement to deter overfishing and address deplete fishing stocks. Consequently, Earth's coastal waters are experiencing increased levels of conflict and social unrest, affecting both regional security and environmental stability. This leads to food insecurity and maritime crime. And this creates a feedback loop where more maritime crime creates instability in the country and more pressure to overfish, which weakens a country's ability to govern its waters. In West Africa, fish represent the single most important source of animal protein. It's a way of life for coastal communities. Our study focuses on Ghana and Senegal, where small-scale fishers have long dominated the fisheries sector, and to this day, between 80 and 90% of fishers in Ghana and Senegal use what we describe as canoes, like the ones on the bottom right, fishing up to 6 nautical miles and beyond. But the number, size, and technological sophistication of those canoes are continuously growing. Trawling vessels are often owned by foreign interests who on the surface appear to comply with local laws by registering their vessels locally and hiring a 75% local crew. Per-seine vessels, like the one on the upper left, on the upper right, are joint ventures between Ghanaian and Chinese, Koreans or Russians, and their landings have increased in the past couple of decades. Over the past decade, numerous studies have concluded that West Africa fishers are experiencing dramatic overfishing. For the first time ever, scientists and fisheries experts in Ghana are now speaking of a complete collapse of the fisheries sectors in 2020. When fishing vessels overfish, they also increase bycatch, which is anything that you did not target but end up catching. Some of this bycatch is discarded overboard, dead or dying, and leads to a complete waste of resources. It is widely accepted by many maritime strategists that food insecurity can lead to regional insecurity and maritime crime. In this map, We plotted data from the International Maritime Bureau on number of piracy, armed robbery, and other criminal activity in the past few decades in Southeast Asia, Gulf of Aden, Arabian Peninsula, and Africa. We can see the increased number of criminal activities such as pirate attacks in West Africa, including Ghana and Senegal in most recent years. Poorly managed fisheries do, in fact, directly and indirectly lead to a greater, more insidious criminal activities and a general weakening of maritime security. This manifests into violent attacks by foreign industrial vessels on domestic artisanal vessels, illegal fishing, forced labor and slavery, territorial disputes, and the use of fishing vessels to traffic weapons, drugs, and other illicit goods. IUU fishing, or illegal, unregulated, and unreported fishing, is a comprehensive term that refers to a variety of activities that violate or are unregulated by the conservation and management measures established under international and national laws. Approximately 37% of fish caught in West Africa is considered illegal or unreported. And there are different types of illegal activities, including dynamite fishing, the illegal use of monofilament nets. But I want to bring your attention to psycho fishing, where the large foreign-owned trawlers catch species that they are not permitted to land, so they work with the artisanal fishermen who adapted their vessels, such as the one on the bottom right, with an empty compartment to buy the fish from the large trawlers to be sold illegally to the local communities. Under Ghanaian law, the minimum penalty for a vessel caught transshipping fish is $1 million. Yet psycho fishing has become so profitable that it's extremely pervasive within Ghanaian fishing communities today. In fact, these psycho fishing canoes may also be involved in other maritime crime activities such as drug smuggling, weapon trafficking, and human trafficking to and from the foreign fishing vessels. One way to alleviate the overfishing problem is by not allowing fishing to occur during the most productive season. Senegal's closed fishing seasons have been relatively successful compared to many similar attempts throughout West Africa. On the other hand, Ghana has had several unsuccessful attempts, one more recently this year in May. Some studies highlight the ecological benefits of closing the season to give the fish a break to reproduce and generate large fish yields. And other studies point to the negative economic effects for fishers that rely on fishing for their primary source of income. Closed fishing seasons are not favored by fishermen. As you can see on the sign on the right, no fishing, no vote. All this leads to what Garrett Harding has characterized as the tragedy of the commons. In terms of implications, at the center of this complex problem, we have increased human population, creating greater demand for seafood and more pressure on the environment. Marine pollution and climate change have impacted the environment in many ways, as discussed in this plenary, exacerbating the situation by changing the species composition and distribution in the ocean environment, all of which increase food insecurity. Fishing overcapacity is one of the most leading causes of this overfishing. This means that we have too many people, too many boats catching too few fish. As fish stocks decline, there's a pressure to fish harder, sometimes illegally, leading to the collapse of fish stocks. This is not only an ecological challenge, but also socioeconomic issue, since 35% of the world's population gets most of their protein from ocean resources. Overfishing, caused by greater demand for seafood due to the increased human population, has led to larger boats using greater technology, fishing legally or illegally in their own country waters or outside their exclusive economic zones, leading to more bycatch. All this can change the natural food web of the environment and also increase the impact to the sea bottom. The large fishing boats sometimes drag nets or large dredges along the bottom, which destroy the habitat. When fishermen don't have enough catches, they don't have enough food or enough money to buy food, so that increases food and regional insecurity, which increases the pressure to overfish. So there is a feedback loop. Desperate fishermen use violence when competing with each other for fishing spots. They can start resorting to criminal activity. to support their families, such as armed robbery, human trafficking, to transport young children to work as slaves in boats. And they use their boats to traffic drugs. In the absence of effective maritime governance, state and non-state actors can engage in or support piracy, illicit commerce, illegal fishing, support acts of terrorism, while exploiting a country's territorial waters and exclusive economic zone. Poorly governed maritime spaces also invite undue influence from predatory states seeking to exploit a country's fisheries, energy, and natural resources. This is a very complex issue which demands holistic solutions through scientific research, monitoring fish populations, cooperation between countries and within communities to enforce fisheries laws and programs to provide alternative livelihoods to impoverished communities. So what can you do about this? You can make a difference through your actions and your voice. Become informed about scientific research regarding the ocean and your environment. The future of the ocean relies on your ability to understand environmental issues and to do something about them. Support policies for environmental protection, such as the development of marine protected areas, marine reserves, where fish and habitats are protected and allowed to recover from overfishing and habitat damage. These MPAs provide a safe haven for species to grow as they start spilling over into other areas where fishermen can catch them sustainably. Reduce your carbon footprint by biking or walking to school and to work whenever possible by recycling and using less electricity. There are several apps you can have on your phone to check which types of seafood are caught sustainably, using environmentally friendly gear and catching species that are not overfished. In many countries, women are often marginalized groups who do not participate in the decision-making process, but they're essential to sustainability of fishing. So advocate for social justice, where people are treated with respect, are given a fair chance to have a healthy life, and are involved in a decision-making process about their environment.
Thank you very much, Dr. Marakovich, for bringing us home with that talk on global overfishing. Overfishing is another one of those challenges facing the world ocean that I find myself extremely passionate about, because I really do believe that it's solvable in our time. So thank you very much, Dr. Marakovich, and thank you to all of our speakers. In summary, today, during our session on human impacts on the ocean, we discussed the top 10 challenges facing the world ocean today and what each and every one of us can do about it. These challenges are ocean acidification, global ocean warming, sea level rise, sea ice loss, coral reef loss, ocean deoxygenation, mangrove deforestation, ocean plastics, noise pollution, and global overfishing. Each and every one of these challenges seems daunting at first, but when we take it apart and discuss every one of these issues separately, each and every one of them becomes solvable. And I want to thank every single one of our speakers today for discussing these issues, explaining the science to all of us, and telling us what we as individuals can do about it. Thank you very much to our speakers, and thank you very much for tuning into this session. Thank you.